Hey folks, welcome to another ND video. In this video, we'll cover many non-destructive principles that, when followed, should help you build a better intuition when modeling non-destructively from reference images or when creating your own designs from scratch. At the end of the video, we'll look at how I applied these principles to a modeling challenge we hosted on our Discord server last month. The result was this terminal based on a concept created by Davey Perkins. We'll cover quite a bit in this video, so grab a drink or a snack and get comfortable. Let's get started. In this video, we'll work through the principles of deconstruction, dimensions, sketching, subtraction, and replication. For each, we'll take a look at a few small examples. Let's start with deconstruction. The idea behind this principle is that any complicated shape is just a series of steps or operations applied to a simpler starting state. But why deconstruction and not construction? Well, typically when we're modeling, we're working from some sort of reference. These references indicate the final state, so we must work in reverse. We have to slowly deconstruct the reference, identifying each step that may have been taken, and continue doing this until we've reduced the shape to its simplest form. Only then can we apply those steps in a forward manner within Blender, producing the final shape depicted in the reference. Now, I'm obviously talking about this in the context of non-destructive or procedural modeling. This may not always apply to destructive or organic shapes, for instance. So let's start with a straightforward example of a final state, a cube. Here, we'll demonstrate one typical operation in constructing geometry, extrusion. Extrusion, simply described, is the act of pulling or pushing geometry in a particular direction, creating new geometry in its path. So, with this cube, can we imagine it in an unextruded state, resulting in simpler geometry? The answer is yes. To think about it in reverse, we could imagine squashing or pushing on some particular area, compressing or collapsing the geometry. You can take its top face, for instance, and push it down towards its bottom face, resulting in a much simpler form, a plane. As we'll see later in this video, if you can achieve this with any given shape, you can presumably model it non-destructively. For most purposes, this is as far as you need to go regarding simplification. I want to make a point though. Unextruding this cube is not the same as squashing it by scaling it non-uniformly along one axis. Of course, scaling any shape on one axis to 0 will leave it flat, but that's not the same as unextruding it. A good way to think about it is that extrusion uses guardrails. This cube's 4 perimeter edges guide the extrusion upwards. Let's quickly examine the cylindrical object next to it. We cannot unextrude it along a given axis as no guiding edges would hold for the entirety of the operation. If you notice this, it should serve as a warning that geometric information is being lost in the process, making it an impossible task for simple extrusion alone. We'll get to know more about this later. Let's go back to the cube. Can we go any further for the sake of this example? The answer is yes. Faces aren't the only type of geometry that can be extruded. Edges and vertices can also be. With that in mind, if we took one edge of this plane and pushed it towards the opposite edge, again, unextruding it, we'd be left with just a single edge. We can still go further. Let's take one vertex of this edge and unextrude it towards the other, leaving us with just one vertex. Since a vertex is the smallest, most straightforward form of geometry we can create in Blender, this is as far as we can go. Given all of this, we now know that if we wanted to create a cube non-destructively, we could pick any one of these simplified forms and perform one or more extrusion operations, resulting in the final geometry. Producing the shape by stacking one or more non-destructive operations allows you to change the parameters of those operations later, resulting in new computed geometry without manually tweaking vertices, edges, or faces. This, in its simplest form, is non-destructive modeling. Now, the point of this video is to go over the principles of thinking non-destructively, not to cover how to use the ND add-on specifically. The ND Deep Dive series covers all of ND's features in depth and is the next best series to watch after this video if you're new to working non-destructively in Blender. I'll leave a link to the playlist in the video's description. We also have several tutorials showing you how to use ND to create different models. Be sure to check those out. Alright, let's look at another construction method, revolution. Extrusion tends to form sharp edges, so it should be a natural hint if you see an object with these qualities, such as our cube. Revolution, however, tends to form rounded or curved edges. Now I'm saying tends to for both operations, as there are exceptions like anything in life. I won't review these exceptions in this video, given that there's still quite a bit to cover, but this may become a series, in which case we'll walk through them in future videos. Let me know in the comments if you enjoy this style of content. Back to revolution. To reverse a revolution operation, start by imagining a seam running down the object's length. If converted into a plane, the seam should cut through the object, mirroring it on either side. You can then imagine the object compressing back on itself in a clockwise or counterclockwise motion around an axis in line with the seam. If we unwind the revolution operation to 0 degrees or remove it entirely, we'll be left with a planar surface. As with the extrusion example, if you can imagine doing this when looking at a reference, it can be built non-destructively, as we'll see here. The most challenging part may be visualizing the appropriate surface, but that comes with experience and time. However, we'll cover techniques to help with this later in the video. Okay, if you've understood all this so far, you're well on your way. Let's move on to another closely related principle, dimensions. The principle of dimensions poses a simple question: how low can you go? Except we're not talking about a game of limbo here. If it wasn't clear from the previous section, being able to model non-destructively involves removing as much complexity and as many dimensions as you can, within reason, from a shape while still retaining enough information to recreate it through a series of non-destructive or procedural operations. A reliable approach to this is to use the idea of an imaginary plane, which is infinitely thin and can cut through anything. When used to slice through an object, this imaginary plane should result in a surface over which the object can be mirrored or extruded, and a cross-section which acts as a diagram or a sketch. We'll cover this idea of sketching in the next section. Take a look at the stock standard cube once again. Here we can visualize one or more of these laser planes cutting through it. For each of them, we can see that it provides a mirrorable surface. It also provides a cross-sectional diagram or sketch. Excellent, these properties are precisely what we want to find. Let's try it with a slightly more complicated shape. Here, we have what is essentially a cube, but with rounded edges. How many laser planes can we use here? Let's draw them. As you can see, only one plane produces the required output with this particular shape, but that's okay. At a minimum, all you need is one of these planes to move forward. If I unextrude the shape using this knowledge, we could reduce it to a simple 2D form with rounded corners. Now, while we have the shape in front of us, I would like to point out another pattern to look for. If I were to rank traditional polymodeling actions in terms of their destruction, bevels would be near the top. Bevels come in two variations, chamfers and fillets. Chamfers are single segment 45-degree cuts, and fillets are multi-segment cuts. In this example, we have a fillet. The good news is that we can perform both types of bevels non-destructively, but there are limitations. The bevels video in the ND Deep Dive series covers the full extent. Bevels are another operation we typically want to undo when thinking non-destructively. The best way to imagine a shape with a bevel undone is to extend the supporting edges outward until they intersect. This intersection is typically where the base geometry started before applying a bevel. If I undo the bevel applied to these corners, you'll see we're left with a very familiar shape, a plane. Okay, let's take a look at another example. I'll pause here for a moment. Can you identify the cross-sectional plane? If you spotted this one, you've got it. This lets us reduce this object to a planar surface and remove the chamfer, again leaving us with a plane. Hopefully, you'll start to see a pattern here. What about this next object? Think about it for a moment. If you're struggling to find a cross-section, that's to be expected. This is an example of an object that doesn't have one. So what does that mean for us? This means that this object cannot be expressed in 2 dimensions. Hence, the answer to how low can it go is 3 dimensions, the same as it is now. However, can it still be simplified? Yes, it can. If we apply the idea of reducing bevels to their starting geometry, we can remove these 2 edge chamfers and end up with a cube. Now, don't let this deter you. While this is a simple shape that's hard to produce entirely non-destructively from a cross-section, it is an oddity. If you remember the terminal I showed you at the start of the video, which looks relatively complicated, it's made using only planar surfaces. So you'll be pleasantly surprised how far you can take these concepts. Now, onto the next section. This is a bit of a revision, but I'd like to emphasize this idea of sketching. A sketch is a 2D or planar surface typically extruded, revolved, or otherwise used to create 3D geometry. Sketching is a technique that's quite commonly used in CAD. Those of you familiar with it will notice that what I'm about to demonstrate here isn't directly equivalent, but similar. Blender isn't a CAD application, so constraints and other typical CAD features are non-existent. As such, we have to make do with what Blender offers us. Still, thinking in a sketch-like manner is the key to working effectively with ND. Let's take a look at this plus-shaped object. If we were to represent this as a 2D cross-section or sketch, it would be a flat, planar cross shape. Easy enough. But can we go further with our simplification? Yes, we can. Instead of creating the shape using a series of strategically placed vertices, we can start with a plane. The trick here is that you can use bevels in unconventional ways. If I jump into edit mode, select the 4 corner vertices and recall the ND vertex bevel operator, I can adjust the bevel's profile to form these concave details. So, once again, a trusty plane is all we need to create this 3-dimensional cross shape non-destructively. What about this next shape? You guessed it, it's just a plane with chamfered corners. How about this next one? Perhaps a bit more tricky. But let's remember what we've covered so far. Start with the obvious details, the chamfers at the object's top and bottom. Let's imagine those have been removed. We're left with a cylinder. Let's simplify it further by reverting the possible extrusion. Now we're left with a disc. There's still too much detail present here. Can we simplify it further, and if so, how? Think back to the example cube with rounded edges. That started life out as a plane with its corner vertices beveled. If we do the exact same thing, but increase the width of those fillets such that their ends meet at all 4 corners, we get a circular shape. If we return those corners to their base geometry, we're left with a familiar shape. Could this be the meaning of life? Is everything ultimately a plane? If it isn't clear at this point in the video, I'm illustrating what you should be doing, either typically in your mind or on paper. The fact that I have these objects already set up and modeled in Blender is just so that we have a visual reference to work with. In a real-world application, when you're ready to model, the geometry you'd start with is this plane. The operations you'd then perform would slowly evolve this plane into its final state, in this case, the chamfered cylinder. If it doesn't make sense just yet, hang in there. I'll go through a working example at the end of the video. Let's now talk about the next principle, subtraction. I describe this process as the CNC process, borrowing again from the CAD side of the playing field. The idea is that sometimes a shape cannot be formed by building up material from a smaller and simpler state. Instead, it's created by subtracting geometry from a larger and more primitive state. This is, for all intents and purposes, how CNC machining works. You start with a solid block of metal, for instance, then you mill parts of it away, revealing a more complicated or interesting form. Let's take this first object for instance. Before demonstrating the concept of subtraction, can you apply any of the principles we've already covered to simplify this shape? Take a moment to think about it. It doesn't seem likely, does it? Any plane you can identify doesn't produce the qualities we're after. We could remove the fillets from the edges, but we'd still be stuck with a broad 3D form. As a side note, sometimes this is all you can do, but we can do more in this case. So, what if instead we unsubtracted, or rather added back, some of the missing geometry? We can identify a missing chunk at the front here. If we could reverse the subtraction of that geometry, we'd be left with a solvable shape. In fact, we solved this shape earlier in the video. The steps should feel rather evident to you now. So if you were given this final shape as a reference, you could deconstruct it in your mind back to a plane. And this is where you'd start. You'd then add the corner fillets, extrude the planar surface upwards, going from 2 dimensions to 3. Finally, you could subtract the final bit of geometry using a Boolean operation, leaving you with the desired final state. The fun part here is that the shape that defines the cutout can also be created non-destructively. If we make it visible, you'll see that it's just a cuboid shape, which started life out as a plane and was then extruded. If everything starts to click at this point, it should feel like you've just swallowed the red pill and entered the matrix. I want to take a look at another subtractive example to highlight another important point. This next example shows a similar looking base object with a hole drilled out of the middle. One aspect that's particularly interesting about this hole is that it has a countersink. In previous examples, I mentioned that when you see a bevel, you can typically undo it. However, if we imagine the shape coming from a plane, where do the necessary edges exist to form this chamfer? The entire top face of this object would be flat if we extruded it from a plane. And that's the key point here. If you're examining an object and can see a series of operations that can be applied to some base shape, but one detail looks impossible, it's usually a good candidate for subtractive modeling. And in this case, that's what occurred. Keep an eye out for it. You'll notice it a lot when studying hard surface references. Finally, let's look at the last principle in this video, replication. Replication comes in a few forms. The first is the replication of an object's specific detail or feature. Much like uncovering whether an object can be reduced dimensionally, if a plane can be drawn such that a detail is mirrored across it, it can easily be replicated. And for this, I've already given you the answer, mirroring. Mirroring can happen across multiple different planes. The second object has had a mirror operation applied across a plane at its base and across the YZ plane. Then there are other forms of replication, such as repetition. In this case, we can see an array of identical objects. There's little point in modeling each of these objects individually. Instead, we can model a single copy first and then array or instance the rest. Arrays don't always have to go in one direction. Repetition can occur in a circular fashion, over an arch, or a more freely defined path. They're just another operation to identify when deconstructing a particular detail in a reference. Okay, so we've covered a fair bit in this video. I would now like to look at a working example by going through the terminal model I mentioned at the start of the video. I'll switch scenes and be back in a moment. So here we have the finished terminal. As proof that something like this can be created entirely non-destructively, I'll select all the parts and turn off the modifiers. The model comprises much simpler shapes, predominantly planar and a few more dimensional. This results from applying all of the principles we covered. Let's step through the process using the original reference image off to the side here. Again, all credit for this concept goes to Davey Perkins. If you're watching this video, Davey, your art is fantastic, and I look forward to modeling more of it. I'll leave a link to Davey's portfolio in the video description. Let's begin. I'll start with a simple detail, this grid of buttons. What's the first obvious way to reduce complexity here? It would be unrolling the arrays back to a single button. Great, now what's next? If I draw out what this button looks like from the top, We're greeted with a familiar shape. It's a cube with rounded edges. The answer should be clear at this point. To model this button, we'll need a plane. We'll then have to bevel its corners and extrude it. The image is a little grainy, but because I can see what appears to be a chamfer around the top perimeter of the button, I'd like to add that in as well. We know that we can add this effect, but it will be applied to both the top and bottom of the object, which is fine with me as the bottoms of these buttons aren't visible anyway. Later, once we've finished modeling and are ready to clean up these buttons, say for UV unwrapping and preparation as a game asset, we can apply all the modifiers and then delete the unnecessary geometry. To finish this detail, I'd then array the buttons along one axis, creating a single row. Then I'd array it again, creating multiple rows. Let's look at this on the model itself. I'll turn off all the buttons modifiers, returning to the primitive geometry I started with. Then, slowly roll through the operations I performed, one by one. You'll see the detail go from a simple plane to a grid of buttons that closely resemble those depicted in the reference. Neat. Hopefully you can see how this all slowly comes together across an entire model. Let's take a look at another detail on the reference. Perhaps these battery-looking things at the back. We can't see the entire battery, just the top bit, so for the sake of time, let's assume there aren't any more detailed parts near the bottom of them. I'll draw out a silhouette of one to start with. If we remember back to the deconstruction section, I showed you an example of a revolution extrusion. That seems to be the most applicable here. We have to identify a seam, which is easy enough with a shape. We can draw one going right down the center. Then, if I carefully erase one side, we're left with a usable profile or sketch. If you were to revolve the sketch around the z-axis, we'd be left with a shape resembling the battery. Let's go over and take a look. I'll turn off all the modifiers. Here's the base sketch I went with. Now, I also used a couple of vertex bevels to curve the piece that sticks up at the top. I then also added a chamfer to this outside corner. I added it as a chamfer and not directly to the sketch because this allows me to adjust this detail later by tweaking the values in the modifier stack without having to manually move vertices around, which would be slightly annoying if I tried to maintain that perfect 45-degree cut. This is a good tip for your own sketches. If you're drawing something out in a sketch and want a fillet or chamfer, add it as a vertex bevel. It'll save you a lot of time and give you more creative freedom. Okay, after that, I revolved the sketch around the z-axis, which created the final shape of the battery. Then, because there were two of them sitting side by side, I ran a mirror operation. And that's it. Let's look at one last example in the reference, which is a little more complicated. The screen hood is a good detail. We must apply several different principles to break it down. The first thing we should look for is a plane that cuts through it, giving us a mirrorable surface. After looking at it for a moment, the only surface that works is running right through the center from the back of the hood to the front. If we look at the back, an extrusion operation alone wouldn't quite cut it, as we have a cutout detail that interrupts the guiding edge. So my brain is telling me that that's a subtractive detail. What about the front? We also have a large cutout. It looks like subtraction again. So, would we have a deconstructible shape if we use some geometrical putty and filled in the holes? It looks like it. If we take the cross-section formed by the plane and draw it out to the side, it looks something like this. Awesome, we have a sketch. If we can start with this and extrude it to the required width, we can add the remaining details via subtractive, aka Boolean, methods. Let's jump over and take a look. Here's the sketch I created. To further enhance it in a similar way to the batteries, I added a few vertex bevels. I then extruded it. I then added an edge chamfer on either side. I then cut out a large hole for the screen. Let's examine the cutting utility. It was created non-destructively using a plane, some vertex bevels, and an extrusion. I then took a similar approach at the back with a few sequential cuts. And there you have it, another detail modeled non-destructively by applying the principles we've learnt to a reference image. If you continued this process for the rest of the model, you'd have a completely non-destructive version of the reference. And that's it. I know there was a lot to go through here, but at the same time, it's really only a handful of principles. Once you've learnt them and taken some time to practice applying them, you'll be well on your way to confidently working in a non-destructive manner within Blender. Now, I'm certainly a purist when it comes to this, so I strive to keep everything as non-destructive as possible. However, there's absolutely nothing wrong with using these principles and ND to create these shapes and then immediately applying the modifiers, continuing to work destructively if you're more comfortable with that. Use what works for you. I hope you enjoyed this video. Please leave a comment if it has helped or if you have any questions. If you want to support us, consider becoming a patron or donating to ND via Gumroad or the Blender Market. Feel free to join our Discord server if you'd like to chat, hang out, learn, and partake in the next challenge. I'll see you next time.